Hi, and welcome to this fifth clip of this AQA Organic Chemistry series. And in this clip, what we're going to discuss is the combustion of some fractions that we can obtain from crude oil. And we saw in the previous clip how we looked at the forces in between two molecules of methane and also propane. So methane being a small molecule and propane being a slightly larger molecule. And what we're going to do in this clip is we're going to look at their ability to combust. So crude oil, as we've said in earlier clips, is a relatively useless substance in the sense that it doesn't really do anything as you find it or as you dig it out of the ground. What you have to do is process that in some way, and that via fractional distillation, allowing us to get these fractions, these collections of compounds with similar boiling points, and allowing us to get fractions, to say, with slightly purer combinations of molecules, which are a little bit more useful than the parent crude oil was. But primarily, most of the uses of these fractions are as fuel. So we have to burn them, and so we have to combust them. And in our combustion equations, we're going to react each of these fuels, methane and propane, both with oxygen. And so, by definition, the products of combustion will be carbon dioxide and also water. Now, because we have a hydrocarbon and we only have a compound made of hydrogen and carbon atoms, we are only going to produce carbon dioxide and water in these examples, and both of them, being hydrocarbons, will produce the same components. They'll both produce carbon dioxide and water. However, we can see that if we were to try and balance these equations, we would have 3 atoms of carbon here, leading us to require 3 molecules of carbon dioxide. We have 8 atoms of hydrogen here, requiring us to balance that with 4 molecules of water. This would then lead us to 6 atoms of oxygen here, with a corresponding 4 atoms of oxygen there. That would lead rise to a total of 10, meaning that we would have to have 5 lots of the diatomic oxygen to give us the 10. 5 times 2. In the same way, the first example would give us 1 molecule of carbon dioxide. I'll write the ones in so we can use them as comparisons. And we would have 2 water molecules. If we add up all the oxygens on the right-hand side of that equation, we would get to 4, which means we would need 2 molecules of water there. And so, what you can hopefully see there is that in order for 1 molecule of methane to fully combust in the same way that 1 molecule of propane will combust, we need an increasing amount of oxygen. So as the molecule gets larger, the amount of oxygen, or the number of moles of oxygen, the amount of oxygen required increases. And so this means that in order to completely combust, it's going to get increasingly more difficult for the corresponding amounts of methane and propane to react properly. And if you use your imagination, if we were to imagine a molecule of C60, and let's say it was an alkane hydrocarbon, that would have 122 hydrogens with 60 carbons. The amount of oxygen, and you could perhaps try to balance this equation, would be significantly larger than the 2 and the 5 that we're looking at here. But what this allows you to do is appreciate why, in the previous video, we suggested it got increasingly difficult for larger molecules to be ignited. And we said that the ease of flammability, the ease of which something can burn, was significantly easier if the molecule was smaller. And so we had the smaller molecules towards the top of the column, thinking about that trend, and we had the larger molecules towards the bottom. Again, as I said in the previous video, propane, C3H8, isn't a really big molecule. It's just bigger than methane for the purposes of what we're doing. It's just a lot easier to write equations and draw diagrams with a C3 molecule than it is with a C60. But propane is bigger than methane, and so requires more oxygen. It means it's more difficult for it to ignite. And so we also see that in the products that we get. Now, if we were to look at these situations, if we produce carbon dioxide and water, we've undergone a process known as complete combustion. And complete combustion will produce carbon dioxide and water as its products. They would come off during combustion as gases, and we will discuss in other clips the downsides of producing carbon dioxide as a greenhouse gas, etc., etc. But in terms of the combustion products here, burning of propane will produce more carbon dioxide, and you could argue that it's a bigger contributor to global warming than perhaps methane would be. Likewise, if we were to look at some other carbon-containing compounds such as diesel and aircraft fuel and power station fuels, which would again be increasingly, so gasoline, so petrol in cars is typically a C8 molecule, octane in size, would have a relatively large amount of carbon dioxide produced. Diesel can be something in the 18 to 20 carbon range, so it would again have an increasing amount of carbon dioxide produced. But as we say here, as the amount of carbons increases, the relative amount of oxygen that is required gets increasingly large and can be increasingly difficult to produce, which means we have this possibility, which can also exist, whereby instead of undergoing complete combustion, we undergo what's called partial or incomplete combustion. And instead of the carbon dioxide being produced, i.e. CO2, we produce CO1. Now, we wouldn't necessarily write the 1, but CO1, or carbon monoxide, as it's also called, is a gas and is caused when we don't get enough oxygen to the fuel, and so it can't get the 5 it needs. It might get 4 or 3, or basically it doesn't get 5. And so this second oxygen here on carbon dioxide can't bond with the carbon, and so we only get this 1 oxygen being produced, carbon monoxide. Now, carbon monoxide is not necessarily a greenhouse gas, but is poisonous to humans. And so if we were to breathe carbon monoxide, it can be poisonous, as carbon monoxide can be uptaken by hemoglobin at the expense of oxygen. And so we have to be very careful about burning fuels properly in the home. So for example, you'd always have to have your central heating gas boiler serviced, or to make sure you've got plenty of oxygen if you happen to have a coal fire or a log fire, ensuring it's got an adequate source of oxygen. It is possible to go one step further and we don't get any carbon bonding with oxygen, and we literally just get the carbon being kicked out as a byproduct instead of carbon monoxide and also carbon dioxide. And because this comes off as a solid, this would come off as soot. And so if you happen to have a coal fire or a log burning fire or a barbecue or something like that, you often see a black powdery residue being left on the side of the fire or on the glass. And this is the carbon which is being burned but isn't getting anywhere near the amount of oxygen it needs, and comes off as carbon, as pure carbon, as a solid. And sometimes when you see the smoke coming out of the chimney, it's quite often the carbon which just isn't getting enough oxygen. If you see a car on the motorway and there's black smoke coming out of the back, if it's trying to drive quickly or something, that's sometimes as a result of being too much fuel going into the engine, and that engine not providing it with enough oxygen at the speed it's going. And so you get the product of carbon produced instead of carbon dioxide. Now, ideally, for combustion, we would want carbon dioxide and water to be produced, because that is complete combustion and it's a much better chemical process. Obviously, carbon dioxide has its drawbacks, as we'll look at in later clips when we talk about the environmental discussions of carbon, but for the purposes of this, we want to produce as much complete combustion as possible, and so we have to ensure that in order to burn, completely combust a fuel, we have this minimum amount of oxygen, and we have to ensure we've got at least that amount to produce the carbon dioxide and water, as opposed to carbon monoxide and also carbon. In each of these carbon monoxide and carbon processes, we would also produce the water as well. That would always be produced as the second product. The one which would change through partial or incomplete combustion would be the carbon monoxide and carbon side products. And so, thank you for that one. In the next clip, we will look at how we can take some of the less useful fractions of crude oil, typically the larger ones, which, as we've discussed here, would be increasingly difficult to combust, would be more viscous to use in a suitable fashion, and if they do burn, they happen to give out a lot of smoke. We'll look at ways in which we can take those products, those fractions which aren't as useful, and we'll look at how to make them slightly more useful and of more demand in the industrial world. That process will be cracking, and we will look at that in the next clip. So thank you very much, and I'll see you in the next one.